It is our great honor and pleasure to have Professor Christopher Consolis from University of Manchester, UK. I'll give a brief introduction here. Professor Consolis did his PhD in 2001 from University of Wisconsin-Madison. He has done a couple of postdocs from STSCI and Caltech. He has been a faculty at University of Nottingham since 2005 and is now at University of Manchester. He has won several awards, including the most cited young space scientist in 2008 and the Philip Leverhulme Prize in 2009. He has led many space-based and ground-based imaging surveys, including Hubble Deep Field and Good Survey. He led the team in 2016 that showed that the number of galaxies in the universe is 2 trillion. He is the lead editor of the Galaxies and Cosmology corridor for astrophysical journals. So I now request him to deliver his talk on new results pertaining to galaxy mergers.
Right. Thank you very much for that nice introduction. So it's nice to be speaking with you guys today, and sorry I can't be there in person. Hopefully one day I can visit. Certainly would like to. But for today, what I'll talk about is galaxy mergers and a study that I've been working on, or a topic I've been working on for now, well, 20 years or so, looking at how galaxy mergers affect galaxy evolution and how galaxy mergers can tell us about other things as well, including cosmology and gravitational waves, etc. And I'll touch on these topics, although this will only really be an introduction to some of these things, which have and can have a much more detailed research and explanations. Okay, so let's jump in. All right, so my talk is going to be observationally based. So there's plenty of theory, and I will talk a little bit about that in various places, but in general, my talk is going to be based on observations and observations of galaxies in the optical and near infrared. And that's mainly done with ground-based telescopes and the Hubble Space Telescope, and very soon the James Webb Space Telescope, which I'm sure all of you have heard about. So the way that we do this is in two different methods. So with Hubble, which you can see the picture on the right here, this gives us very deep pictures. In fact, the deepest pictures we have, images we have of early galaxies comes from Hubble. However, Hubble has a very small field of view. The size of this picture here is only about a 1 arc minute in size. That's very tiny on the sky, okay? And the left shows a way to complement that, which is to take very deep ground-based imaging. So by ground, I mean telescopes on the ground. So things like the VLT, Keck telescope, but also even 4-meter telescopes. And the advantage with those is that you have very large fields of view. That is, you can take fields which are about a degree in size rather than an arc minute. All right. So roughly a factor of 60 to 100 times larger field of view. The issue with doing these type of observations from the ground, however, is that you can't go very deep just because of background levels and just because of the inability to obtain high quality data at a deep level, simply due to you would have to expose like for a couple of years to match some of the depth you get with Hubble and the near infrared due to the high background noise. So these two methods complement each other, and I will talk about using both of these throughout this talk. And these are some of the telescopes, and I've already mentioned Hubble here on the right, but also there's UCURT, which is a UK infrared telescope, but which is no longer owned by the UK or run by the UK. And then there is ESO Vista, which is another telescope, which is part of ESO, hence the name. And that is also an infrared telescope. And it's been used to do very deep fields, which I'll talk about in a moment. All right. So the observations which tend to show us that there might be something going on with galaxies merging and evolving from mergers originally came about due to observing the morphological evolution of galaxies. And what we know is in the local universe, you have most galaxies are either, most bright galaxies are either spirals like the Milky Way or elliptical galaxies, like, massive, like M87, like what you see in clusters of galaxies. And those make up by far maybe 97, 98% of all nearby galaxies that are bright or elliptical or a disk galaxy, a spiral galaxy. But when you go to higher redshifts, and this plot shows it, and so does this, these are basically the same, showing the same thing, is that when you go to the highest redshifts, this is redshifts 1 to 3, and hopefully everybody knows what redshift means, but basically higher the redshift, the further back in time you're looking, the earlier part of the universe that you're looking. When you go further back in time, further back in redshift, you find that the galaxy population is dominated by peculiars. Okay, so this part of this diagram shows the fraction of galaxies. This is just the number of galaxies of that type divided by the total number of galaxies. And there's a selection here such that the galaxies have a mass greater than 10 to the 10 solar masses. So these are pretty massive galaxies. So they're analogous to the most massive galaxies in today's universe. You see that the peculiars dominate this population, whereas this one is the spheroids. So these are like ellipticals, and these are disk galaxies. You see that there's a gradual transition to having fewer and fewer classical Hubble types as you go to higher redshifts. You can see it here plotted in a very similar way. Here you see the disk galaxies decline a lot, ellipticals decline a little bit less, but still decline, and then the peculiars here go up quite a bit. Okay, so we know that peculiar galaxies look very strange, and they dominate the early parts of the universe. And this is kind of what we mean by peculiar galaxies, are things that look like this. And these are obviously, almost all of these are obviously galaxy mergers. Okay, they're in some phase of two galaxies smashing together to form a new galaxy. And so this process of galaxy mergers doesn't happen instantaneously. It happens over maybe a billion years, 1 gig a year. And the light in the galaxies that are merging together gets distorted. And this is what we see here. And this is what we mean by peculiar. But there are perhaps other ways in which you can make a galaxy look peculiar. It doesn't have to be necessarily from a merger, right? You can have lots of star formation, making the galaxy look very spotty and clumpy, or you can have other features. They used to think that astronomers in the 1960s used to think that a lot of these structures were formed by magnetic fields. You can imagine that, maybe this is a magnetic field where the ionized structures are being collated around the magnetic field, or that structure is forming around the magnetic field. But now we believe that this is all due to the merging process. There's lots of evidence that that's happening, including from kinematics, for example. We know that these are kinematically merging galaxies. But at high redshifts, we don't have necessarily all that kind of data, so we don't necessarily know just by looking at morphology that these galaxies are undergoing mergers. Okay, sorry. So what we did, and others have done over the years, have come up with ways of classifying galaxies in an automated way, a quantitative way through structure, to find systems that are merging. And this is one example here on the left. This is quite an old paper now, where what we did was look at the merger history for galaxies in the Cosmos field, which is one of the biggest HST fields. This is the redshift less than 1, and then the Hubble deep field here, and the Hubble ultra deep field. And you find using this CAS method, we're using the asymmetries and clumpiness of the galaxies, which I unfortunately won't have time to talk about today, but it's a methodology that's been well established for quite a while now. But it finds galaxies undergoing mergers based on their structure, do a quantitative method of measuring the structure itself. And you can see here that if you quantify galaxies as mergers, that the merger fraction increases as you go up to higher redshifts. And by the time you get to redshift 2.5 up here, the merger fraction is about 40–50%. All right, and you can see that in other ways as well, through looking at galaxies in pairs, which I'll talk about in the next couple slides. And there's other morphology ways here, and there's a lot of points here. These are just different studies, but in this plot here, you can see that as you go to higher redshifts, indeed, the merger fraction is increasing. So all the methods that we use have shown that the galaxy merger fraction of galaxies merging evolves as 1 plus z to the 1 to 3 power, and that goes up the redshift of 3. Okay, and that's been pretty well established now by many people over past 20 years or so. Okay, so what we wanted to do, and we started this a couple years ago, is look at what is the merger history of galaxies, but instead of using morphology, use another method, which is pairs of galaxies. So there's two ways of finding mergers. You could find it through galaxies that are undergoing an active merger, through the structure being distorted, or you can see it two galaxies close together that are going to merge soon. All right. If you have two galaxies close together by dynamical friction, they will eventually merge and form a new galaxy. Okay. And so what we wanted to do was use the largest surveys of the deep universe, and this is all done from ground-based imaging, where each of these fields, and here are the three fields: Ultra Vista, the Ultra Deep Survey, and Video. And the details of these are not really important for this talk, but these are just the three deepest near-infrared surveys done from the ground, and they're all about a square degree. This one is exactly a square degree. Video UDS is a bit smaller. Ultra Vista is a bit bigger. So in total, we have about three square degrees, a little bit more of the sky covered with these very deep near-infrared pointings. And the key thing about the near-infrared is that you need the near-infrared to measure distant galaxies' redshifts and also their stellar masses, and also to just find them. Because if you look at only the optical, as you go to higher redshifts, the optical, because of the redshifting of the universe, because of the expansion of the universe, light's all redshifted, and what you're seeing in the optical is often the UV, ultraviolet light, because of the redshift. And so if you look at ultraviolet light, galaxies can often vanish, or they can become very faint, because you need star formation without dust to see a galaxy in the ultraviolet. And so that's very rare, especially for very massive galaxies, which is the ones that we're interested in for this kind of study. Okay, so REFINE stands for redshift evolution, formation, and extragalactic systems. So that's our forced acronym. Everybody has one these days. And we basically re-reduced this data of all three of these fields, and then measured the redshifts and the stellar masses of all these galaxies, and looked for systems that were in pairs. Okay, and so when I talk about redshifts, what I mean is a photometric redshift. I'm sure people have heard of these before, but in case someone is unfamiliar with it, it's basically the idea that when a galaxy is more distant in the universe, it's being redshifted, and it's being redshifted not only its emission lines, which are traditionally used to find redshifts based on spectra, but also the whole spectra is being shifted towards the red, and so the individual magnitudes of the galaxy are different when you look at the galaxy at higher redshifts. And by looking at how the magnitudes of galaxies are distributed as a function of wavelength, called the spectral energy distribution, or SED, very commonly called, you can figure out how far away that galaxy is in this redshift based on its spectral energy distribution. And you can just think of it as, if you have the same SED, redshift 0, then a redshift, if you go to higher redshifts, take that galaxy at higher redshifts, then that SED will just shift redder and redder and redder and in time. And if you know the galaxy has that SED, then you can figure out the redshift based on at what point in the spectrum you're seeing those magnitudes that you would have at redshift 0. That's the basic idea. Okay, and then we measured the masses, and this is stellar masses. And so this is not dark matter, this is just the stars. And that's done in the same way you do the photometric redshift. You're looking at the light coming from the galaxy, and you can figure out what is the mass to light ratio of the galaxy. And again, this is a stellar mass light ratio. And then from that, you can figure out how much mass is in the galaxy and stars that produces the light you see. Okay, and these are all well described processes that have many detailed papers and have been checked and calibrated throughout the years. So I won't go into it in any more detail, just to say that that's what we have done. And then we've looked for galaxies that are in pairs. That is, galaxies that are close together on the sky. That is within either 20 or 30 kiloparsecs. So we did both of these things. And that distance, 20 to 30 kiloparsecs, is important because that basically gives you some time, that gives you some reasonable amount of time for the galaxies to merge. So if they're further than that, like 100 kiloparsecs or a megaparsec, then the dynamical friction timescale can be quite long, too long to actually be a reasonable way of finding the galaxy to merge within a reasonable amount of time. If you do just the dynamical friction calculation using like Schrödinger's formula, for example, you would find that 20 to 30 kiloparsecs gives you a time scale of merging of about a gig a year. So that's a reasonable amount of time, right? We don't want time scales that are like 50 gig a years, because that's longer than the age of the universe, and that's what you get if you have large distances. Okay, so that's the idea. So what we can do with this, and this just shows kind of an example of how this works. You have here a picture of the expansion history of the universe. Excuse me. You have the Big Bang up here, and then you have present day here. And so Refine is telling us about what's happening through most of cosmic history. But CANDLES, this is an HST survey, Hubble Space Telescope, can tell us about the very early stages of this formation. And I'll talk about both of these telescopes and sorry, both of these surveys and what they're telling us about the merger history. Okay, so let's just jump into the plots. Sorry. So if you look at this, and this is just one example of this. If you look at the data and you do exactly the process I just said, you look for galaxies that are close together and they have a mass greater than 10.3 or between 9.7 and 10.3. So this is high mass at the bottom, and this is kind of a lower mass range at the top. We're more complete at the higher masses, simply because higher mass galaxies are brighter, therefore they're easier to find. You can see already here, if you look at these black points, that as you go up to higher redshifts, all the way to redshifts of 6, this is the CANDLES fields, you can see that the merger, the pair fraction, that is the fraction of galaxies in pairs, continues to increase as you go to higher redshifts. And if you look at the other surveys, so this Monday points here, these are the refined points. These are the color points down here, redshifts less than 3. And there's some other surveys we plot on here as well. They kind of agree with the Hubble Space Telescope data, which is good. And you can see it up here as well, that there's a pretty good agreement between different surveys of an increase in the merger history as a function of time. So we do see, when you look at galaxies in pairs all the way out to redshifts of 6, so this is only maybe a gig a year after the Big Bang, that we're seeing an increasingly large number of galaxies which are in pairs as you go to higher redshifts. All right. So that's kind of the main observation of what we're getting when we're doing these studies. However, what we really want to do, and this is kind of where we start getting into the physics of this and the astrophysics of this especially, is what is the role of mergers in forming galaxies? So we have a merger fraction or a pair fraction, but we don't know what that merger is doing to the galaxy, right? So we know that they're there, but are they happening often, or are they happening, just once in the history of the universe? We don't know how often these mergers are happening. We know the merger fraction, but to convert it to a merger rate, which is a time scale of the mergers, like how many mergers you have per unit time, you have to understand the time scale of the mergers you're seeing. That is, you have to know the process time. So if the time is very short, then the merger rate is very high, because if the time scale is very quick, then if you have a high merger, or if you have a merger fraction, for a given merger fraction, if the time scale is fast, then obviously you must have a lot of mergers happening to keep that merger fraction high if the time scale is short. So that's the basic idea, excuse me. And so the merger rate is the merger fraction divided by the observational time scale. Okay, and this observational time scale can come, again, in the old days, people would just use the dynamical friction formula and would just get an analytical number, just look at galaxies in pairs and say, okay, they're separated by this, they have these masses, they have we can estimate their velocities, then we know the time scale. But nowadays, we can use things like very sophisticated galaxy simulation. So you can look at things like the Illustris simulation. This is a very modern, very highly computationally based simulation, hydrodynamical simulation of galaxy formation. And you can use that kind of simulation to determine the time scale of galaxies in pairs. So you just find pairs of galaxies in the simulation, and you just find out how long does it take for them to merge. And this includes dynamical friction, dark matter properties, baryonic physics. So it includes all the stuff. It's sort of a empirical way of doing time scale using a simulation. Okay, and what we get is this. So ignore most of these points on, or most of the features on this plot for now, and just look at the black points. This is the merger rate. So this is the number of mergers happening per galaxy per gigayear. So as an example, here is 10 to the 0, which is 1. So you have about 1 happening every gigayear, 1 merger happening every gigayear for galaxies at this mass range here at redshifts about 1.5. And it goes higher as you go to higher redshifts. And here we have upper limits simply because we are incomplete for that mass range at these high redshifts. But for the higher masses, we can go all the way up to redshifts of 6. And here we're getting almost close to about 10 of these mergers happening, a little bit less than that, per every gigayear. So merging is really becoming quite common as you go to higher redshifts. That is, in the very early universe, the density is very high. This makes sense, of course. The universe is very dense, very early in the history of the universe. And the density goes as 1 plus z to the third. So as time goes on, the density declines in the universe. And you have more mergers happening as a result. So that intuitively makes sense with the cosmology. And I'll just say, and I'll come back to this, is that there's also another way to measure the mergers, which is to the merger rate, which is to do the merger rate per unit volume. Okay, and that's simply the same kind of quantity here. We call this gamma. It's the merger fraction times the number density of galaxies. That gives you the number density of mergers divided by the merger time scale, and that'll gives you in these units of per gigayear per co-moving megaparsec cube. And I'll come back to that in a few slides. Okay, so one of the things that I forgot to mention, so apologies, is that these mergers here are major mergers, something I always forget to mention in talks. That means that these galaxies are merging in this plot with galaxies of similar mass to itself. That is, it's within a factor of 3 or so. So a third of the mass or higher, then the galaxy is considered a major merger because the galaxies have similar mass and are merging together. What you also have is minor mergers. And minor mergers are simply just merging with something which has a third of the mass or lower. So 1/4, 1/5, 1/6, 1/10. And if you want to go further down, 1/100th, as much as you want. Of course, observationally, we can't measure all that, but we can get down to about ratios of 1 to 10. All right. And when you do that, you find, and this is the minor merger pair fraction here. This solid line is the fit to the data. These are the different fields that we were looking at. And this is for 10 to the 11. So these are quite massive galaxies here. And this is the corresponding major merger pair fraction. Okay, that's u to the 1/4. So actually it's 1/4, sorry, not 1/3, 1/4 limit. So this line here is 1/4 to 1/10, and this is greater than 1/4 here. You can see that it's much higher than this line here. So that is the minor merger fraction is much higher than the major merger fraction. That is, there's more minor mergers in progress, let's say. Doesn't mean there's more happening because the time scales could be different, but there's more minor mergers in progress at all redshifts that we can probe this to. And we can only go up to redshifts maybe 2.5 or so for this at the moment. Otherwise, they're just upper limits. Okay. So again, the question of how important minor mergers are depends on not only how many we see, but the time scales of those mergers. That is how long it takes those mergers to occur. Okay. So this is an important thing to keep in mind. Before I get into that, let me just finish with this. But the key thing about that, let me just reiterate this, is that the minor mergers, even though they're more common, they have only a similar effect to it's a similar number of mergers as the major mergers, because the time scales for minor mergers are much longer than they are for major mergers. And if you just look at the analytical dynamical friction formula, you can just see that if you have two galaxies that have quite a differential in mass, the time scale for the merger to happen will be longer than if they have a similar mass. And so even though you have a higher fraction of these minor mergers, the effect of the number of mergers is quite similar, simply because the time scales are much longer for the minor mergers. Okay, so that's a very quick guide to what we're doing, what we've discovered with these mergers. Now, one of the traditional ways, the more traditional way, I would say, of looking at galaxy evolution formation is to look at the star formation rate. And of course, there's famous plots like this. This is the star formation rate density is a function of redshift. And you can see here, this is in solar masses per year per co-moving volume. And this is today. So you have quite a low star formation rate compared to redshifts of 2, where you have a peak, and then it goes down as you go to higher redshifts. All right, so this is just the number of stars being formed per unit time, in this case per year, and it's in a given volume. Okay, co-moving volume. So this plot tells us that the star formation rate density increases here and then starts declining again. And there's lots of things we could talk about with this, but for the interest of time, I'm just going to discuss it in terms of galaxy formation. What this doesn't tell us, though, is what are the individual star formation rates of galaxies. It tells us that overall galaxy population, star formation is increasing and then declining. But in terms of which galaxies, which masses of galaxies are forming these stars and so on, this plot doesn't necessarily tell us that. But that's something that we can look into. And ultimately, what we want to do, one of the things that we can do to compare or to understand galaxy formation is to know what is the more important process in forming galaxies. Is it the star formation rate, or is it these mergers? Okay, because these are the two main ways that we form galaxies, right? You have to form stars through star formation, right? You can't form stars through mergers. You have to merge existing stars from two different galaxies. But for star formation can obviously build all the stars in the galaxy. But if you look at, let's say, the end product of galaxy evolution today, just look at all the galaxies in the local universe, some fraction of those stars in those galaxies form from star formation in the galaxy that it's in, and some of them form in star formation in another galaxy that then merged. Okay, so the process of galaxy formation isn't just star formation, it's also the assembly of mass due to mergers, right? So we want to know how much of the stars, how much of the mass of stars and galaxies form through what you might call in situ, that means inside of the galaxy, star formation, how much happened by bringing in stars from other galaxies. Okay, and now we can really start to answer that question with the data that we have. Okay, so this is the same plot I showed before, but now we can look at the other parts of this diagram. And the thing you look at here is the right-hand side. So this is the specific mass accretion rate. So this is the amount of mass brought in through mergers into galaxies as a function of redshift. And so basically what it is just the amount of mass brought in through mergers divided by the initial or the mass of the galaxy. All right. And so you can see here that at the higher redshifts, and it correlates with the merger rate just due to the way that it works, the way that the formulas work. You can see that at the highest redshifts here, that the mass accretion rate is very high, as it is the merger rate. And what I've also plotted here is the specific star formation rate. And so what that is just the star formation rate of galaxies at these masses here. So they're all selected by these masses divided by the mass of the galaxy. That's what the specific star formation rate is, SSFR. And so the important thing is that you can compare this green curve here to the individual points, and you can see that there is a similarity here at the highest redshifts, but as you go to the lower redshifts, you're getting that this green part is much higher than the black points and the other points as well. And that's because the star formation is more important of a process, at least according to this plot, for putting mass into galaxies than the mergers themselves. But at the highest redshifts, you have that the merger process is becoming equivalent to, or maybe even a little bit more important than the average star formation process for assembling galaxies. So very early galaxy assembly And this only goes to redshift of 6. We'll be able to do this with James Webb at higher redshifts quite soon. That at redshift 6, you're still getting, you're already getting that the mergers are becoming more important than star formation. But star formation tends to be a more important process here as you go to lower redshifts. Now, caveat about this is that this doesn't include, or it doesn't consider the fact that the star formation rate can be triggered by the mergers themselves, right? So one of the key things about mergers is that when you smash two galaxies together, there can be lots of cold gas in these galaxies that can then trigger star formation. And so star formation here, some of the star formation will be triggered by mergers themselves. But this is a very complicated thing to untangle, and that's not something that we've done yet. Just something to keep in mind when looking at this. All right. Okay. So just to say that, we see evidence of this merger process occurring in other ways in galaxies as well. One of them is that you see that galaxies increase their sizes as they go to lower redshifts from higher redshifts. And this is just 3 ways of parameterizing sizes of galaxies. This is just different so-called Petrosian radii, which are just radii based on the surface brightness of the galaxy that is independent of redshift. There's lots of discussion I could give about that, but essentially it's a consistent way to measure the radius of a galaxy, which is not biased by redshift. A lot of methods are, and you can see that as you go to low redshifts, the sizes of these galaxies, in particular, if you look at the outer radii here, they grow. So galaxies are growing not only in mass but also in size, and this is at a given stellar mass. And so if galaxies are growing in size, it's a good sign that there's merging happening, because mergers can not only make galaxies grow in mass, but they can also puff up the galaxies in size. Many different models and simulations have shown that mergers do both. They make galaxies more massive, but they also make them larger, and they increase their size faster than they increase their mass. And so you can see that here is just a differential here in the radii. As you go to higher redshifts, lower redshifts, you get a higher increase. There's a bit of noise here for these lower redshift, but still you can see that there's a general increase as you go to lower redshifts in the differential size with time. And this is also evidence of an inside-out formation, because the inner radii doesn't change so much, but the outer radii does. This is the blue is the outer radii. This is this indication that it's not the bulges or the centers of galaxies that are growing, it's the outer parts that are growing. And that's where you would see a lot of the mass be deposited from galaxy mergers, especially minor mergers. Okay, so some of the more recent work that we've been doing has included using machine learning, using deep learning. And this is something done by my PhD student, Leonardo Ferreira. And what we did was we took the Illustris TNG 300, and this is for those who aren't familiar with this simulation. This is the very sophisticated modern simulation of galaxy formation at a high resolution, and all the galaxies you're seeing here in the picture are simulated galaxies. They're not real galaxies, and you can divide them up based on the simulation. The simulation tells you exactly what a galaxy is doing, into galaxies before they merge, after they merge, and when they're not merging. And so by using machine learning and deep learning on these images, you basically do supervised learning. You can train a machine through a CNN technique, convolutional neural networks, to find these galaxies in these various stages. That is, before a merger, post-merger, and then also a non-merger. And then you can use that to apply that training onto real data. And that's what we did. And this is what we get. So these different color points: before merger is blue, post merger is the orange, and then all mergers are the green. So you can see here that for the fraction, you get these points here, and the best fit is this line here. And if you look at the merger rate, you can see that the merger rate derived from these simulations, machine learning applied to the simulations, agrees very well with the results that I just showed, which basically are these last 3 things: the Duncan and the Mundy points of what I had just shown in the previous plots. and that's the red here and also the gray. So there's a pretty good agreement. And why is this important? So, you could say, well, you're looking at this and you're getting the same thing. So what? Well, what is that? Why does that matter? Well, it matters because we're looking at galaxy mergers here in two completely different ways. So one of the things that's very critical about this, and this is true for anything in science, and especially with astronomy or galaxy evolution, is you're measuring something, but you don't know if you're measuring it right. You don't know if it's being done correctly. You don't know if you have systematics or biases in your measurements. So it's always good to have a alternative complementary approach to try to measure the same thing and to hopefully be consistent. And if you're not consistent, then something is wrong, right? Either assumption is wrong that you're measuring these things, or you're measuring it wrong, or something else. So you need consistency. And so because we're using machine learning on images and also looking at galaxies in pairs, those are two totally different ways of measuring mergers, right? Because a galaxy in pair is not the same thing as a galaxy which has undergone a merger, because that would just be a distorted galaxy. And this is what the machine learning is finding. And so the fact that they're consistent is a good sign that we're actually starting to measure these merger rates and merger fractions accurately. And this is something I'm working on a little bit, is that this is consistent with a dark matter dynamical friction interpretation. So there's a lot of talk amongst some people about modified Newtonian dynamics, etc., about alternatives to dark matter, which are fine. There's good things to talk about. But I would argue that these results are strong evidence that there actually is dark matter, another piece of evidence for dark matter, simply because if you have galaxies in pairs and there is no dark matter, then the galaxies in pairs can stay in pairs for a very long time. They don't have to merge, right? Because you have a dark matter halo in these galaxies, that will produce the dynamical friction, right? You need to have this sea of dark matter to produce the wake, which then slows the galaxy down. That's the whole idea behind dynamical friction, and that will make the galaxies merge. But if you don't have the dark matter particles in the outer parts of the galaxy, then there's nothing to cause the friction of the galaxy orbiting it, and it can orbit it for a very long time. It may never even merge. But because we're seeing consistency between pairs and the galaxies that have already merged due to structure, it's a good sign that there's a dark matter. There must be a dark matter or some kind of outer material within these galaxies that produces the dynamical friction. Okay. All right, so let me go through the next stuff a little quickly because I'm running out of time. So one of the things that the merger results bring up is you can produce mass increases in galaxies due to mergers, but it's not enough to account for all of the increase in mass we see in galaxies. And in fact, if you look at the other plot I just showed, the star formation rate is the dominant producer of mass in galaxies at lower redshifts. And so the question is, where does all that gas come from? Where does all the baryons to produce that star formation come from? And because it's not coming from mergers, because there's not enough of them to keep replenishing galaxies of gas that's then producing star formation, because you need lots of star formation. And I'll show the reason for that in a second. All right. So one of the things you can do with this is you can ask, well, how much gas is in these massive galaxies? This is something we did a few years ago in the Goods-Nickma survey, another survey I led about 10 years ago. And when you measure that for these, and these are very massive galaxies, these are greater than 10 to the 11, you find that the gas mass fraction, which is just simply the fraction of mass that's in gas, that is the gas mass divided by the stellar mass, is maybe 10-15%. And this is consistent between redshifts of 1.5 and 2.5 to 3. And this is another version of this, where if you look at this is from Minucci et al. As you look at higher masses, you find that the gas mass fraction is lower. And so these galaxies here are in this part of the diagram. This study didn't even get to those high masses. So why is this an issue or a problem? Well, this is a problem because these galaxies here, these massive galaxies at redshifts 2.5 to 3, are easily doubling their stellar mass over this epoch. over this time scale. However, if you only have 10, 15% of your stars in gas, right? Then if you convert all that gas, this mg, into stars, you're only going to add 15% or so to the mass. And that's not counting for stellar evolution processes, which will then deplete the mass even more. All right. So there's a problem, right? Because you're not getting enough mass of gas through mergers, and you don't have enough gas mass in the galaxies already. There must be something which is bringing gas into the galaxies. Okay. So how much is that? Well, you can use very basic formula like these. Won't go into this in too much detail, but basically you just have continuity equations like these here, where you have the stellar mass and the gas mass as a function of time. You have the initial masses here. This is what the 0 means. Then you have the amount of mass brought in through stars. This is stars through mergers. Then you have the amount created through star formation. This is star formation rate times time. So this is simply just SFR times T is the amount of mass. The gas mass is the amount originally there, the amount that you bring in through mergers, which we can calculate, the amount which is accreted in through a process external to mergers. This is what we're kind of want to get after, is how much extra mass is being added to galaxies in the gas phase. And then minus the amount driven, the amount removed from star formation. Okay, now we can solve these equations because we know this is basically true, that the gas mass fraction at time for these massive galaxies between redshifts of 1 and 3, the gas mass fraction is constant, right? This is this plot here. This is basically constant. So the mass, the mg over m star, is the same throughout this epoch. Okay, so this is basically observed condition. This might be a little bit, might be able to put a little bit of change, but it's not going to matter that much. All right, so then you can just solve these equations for MGA, right? So just basically, what I would call high school algebra. You can just solve for MGA, and it gives you this formula here in terms of mg, and you're putting in some of the known quantities here, because you can divide by basically m star throughout this equations, and so there you can normalize everything, and then you get MGA is equal to some constant times mg naught plus star formation rate times time minus the mass brought in through mergers and gas. Okay, and then you further go through the math here and divide by, as I said, m star. So you put things in ratios that we know, and then what you get is that the amount of gas you need to bring in through accretion, through some kind of process like cold gas accretion or something like that, is about the order of the mass of the galaxy itself. So you need to bring in a huge amount of gas, which is not brought in through mergers, through something like cold gas accretion, or you have hot gas maybe in the halo, which is cooling. We don't really know, but we know that this extra amount of gas must be brought into the galaxy from the intergalactic medium or the CGM, or some process. This doesn't tell you how or where, but it tells you that there's something something coming into the galaxy, and this results in basically a accretion rate of about 83, about 100 or so with the error bar solar masses per year. So that's quite a lot. So this is a huge amount. This is higher than the star formation rate for these galaxies of gas being brought into these systems. And now we can do this as a function of redshift. And as you can see, that the gas accretion rate here, consistent with 0 for most of the history of the universe. This basically here is about, 10 gigayears of the history of the universe. It's about basically 0, but a redshift 1.5 and greater, you're getting very large numbers of gas accretion needed to form galaxies. Okay, and why does it decline? How does it decline? We don't know that. Maybe it's something to do with feedback, not allowing more gas to fall in, etc. But we don't know for sure. Okay, so that's how we think galaxies are forming. Is bringing in galaxies through mergers, but also through star formation and also gas accretion. Okay, so we have some good idea of what the processes are. There's a lot more questions about those, but that's the basic idea. And one of the things that we can also do with mergers is look at the merger rate density. So I talked about this a little bit in the beginning slides, but merger rate density is the number of mergers happening per unit time, per gigayear, per co-moving megaparsec. And when you do that, what you find remarkably is that it's fairly constant. All the way up to redshift of 6, you get a constant merger rate density. So this is the number of mergers happening per unit volume, per unit time. And the cool thing about this is that you can then use this to do predictions for gravitational waves, because we know gravitational waves are produced from massive galaxies that are smashing in together, like the common thing nowadays, black hole mergers, or black hole neutron stars, or neutron stars merging together. But in this case, we're looking at galaxies merging, but also the fact that these galaxies will have massive black holes in their center because they're very massive systems, and then those black holes will eventually merge. And so by getting an idea of the merger rate of galaxies, you can get an idea of the black hole, supermassive black hole merger rate, because those galaxies will drive the black holes to merge in the centers after some time. Although, of course, you can debate how long that is, but after some time, many of them will. And we know that LISA will discover basically all supermassive black hole mergers at z greater than 3, and all the way up to maybe z of 15, where you have these galaxies. And then you have pulsar timing arrays, which can look at basically the time period between pulsars and how they differ due to gravitational wave coming in to a system. And that essentially gives us an idea of the background gravitational pulsar timing array experiments of a background. And LISA will detect individual events. And so it's a very simple plot here, but this shows on the left here the cumulative number of gravitational wave events that we would see based on the merger history that we just talked about. Okay, you just integrate through time or through volume, sorry, all the mergers that would happen as a function of redshift, and this is per year. And you find that if you look at this, that what we're getting, and this is extrapolated here, so you may have 2, but if the redshift is 6, what we can observe, you would find a little bit less than 1 event per year. That is, one of these merging galaxies would show that we would get about one of these gravitational wave events per year due to 2 massive galaxies merging together. And over here is the gravitational wave background from pulsar timing arrays. This is a study we did a few years ago. And this is the current limit that we have on these measurements, but it's not quite at the level that can be detected, but soon it will. And so all these mergers are producing a background, gravitational wave background that can then be detected in principle by these pulsar timing arrays. And that will be possible hopefully soon. Okay, so I just wanted to finish a little bit about high redshift in the future. I'm going to go through this quickly because I don't want to be too long in the talk here. But a very high redshift, and I already talked about the mergers, and that's something that we definitely want to continue to do with James Webb. But also there's other things like looking at galaxy clusters is something that we did a lot recently with another PhD student, and looking at the mass function of galaxies. That is the number of galaxies per unit mass. This is a paper from a former student of mine, Ken Duncan, who did some of the merger stuff as well. And the very difficult thing about this is something that we're going to do with Webb as well, is look at clusters of galaxies for lensing. So these galaxies will lens background galaxies, and then you can really study some of the faintest, earliest galaxies. And this is a very difficult process. Removing all these foreground cluster galaxies is very difficult, but we were able to do it. Basically working on it for over a year and a half. We finally managed to do it. And when we did that, we were able to measure the galaxy mass function all the way up to redshifts of about 9 or so. So this shows that work here. And what you can see here, and this is redshift of 9 here, is that the mass function can be measured. And this is the lower redshift mass functions. And so there's galaxies at redshift of 9. They're fairly rare, but there's still a lot of them at the lowest masses, which means that the mass function is very steep, which means that there's a lot of faint galaxies and a lot of faint low mass galaxies in the very distant universe that we still have yet to study in any kind of detail. And this suggests that this is another reason why mergers are really important in the early universe, simply because you have so many of these low mass galaxies that they're rapidly assembling galaxies through this process of merging. And this is a prediction of cold dark matter. This is where the cosmology comes in, because one of the things that CDM predicts is that you should have lots of low mass objects in the early universe, which then merge together to form larger things. And it seems like from the observations that we're getting of having very steep mass functions as you go to higher redshifts, that there are lots of these little galaxies that are in the early universe that are now forming the larger galaxies. And one of the things that we can do with this is measure the matter density in the universe. That is the stellar mass density of the universe. You can see there's a nice gradual trend here where you're building up the mass as you go to lower redshifts. Although what we found is that there's actually maybe a plateau here at redshifts 8 and 9, where the increase is maybe not as steep as you might think. That is, the decline is not as high as you go to higher redshifts. And this might be because of a very rapid merger process happening at these very early times that are building up the masses of these galaxies in a way which makes them easier to detect, which makes them easier to account for their mass, and builds up the mass faster than you might project here. That is, this might go like this, and then it might kind of flatten out. We don't know yet, but we will know with Webb. This is basically the best we can do until Webb. Okay, to the future, as I mentioned, is James Webb and also the Euclid Space Telescope. So I'm very involved with both of these projects. I'm on various GTO, GEO, and early release data, and I'm one of the science legacy leads on Euclid. And so there's lots of things that we have in store for these telescopes. And just to show you a simulated deep field of what Webb will look like this. And this will be a very beautiful thing to see, but will be tricky to analyze because you're getting such deep fields that the galaxies are now overlapping. And when that happens, it's very difficult to disentangle the light from different galaxies. And so this is something that we're actively working on how to do. And one of the things that I'm very heavily involved with is the Webb Medium Deep Fields Guaranteed Time project. So we'll get some of the first data from the telescope. And we're looking at these clusters again, and we're going to look for these gravitationally lensed objects that are magnifying the sources and making galaxies easier to study in a distant universe. And so we're very excited about that. And these are some of the examples of things that we were going to study. And just to say that the reason why some of the ones that we picked is because they have a low background. So some of these clusters here are difficult to study because of the light in the foreground, which makes it difficult to see background galaxies. But we have found clusters that have a very low light level in their background that makes them easier to find. This is just a simulation of finding objects, where here at the this red line shows a typical example where you're only finding 50% at different magnitudes and then drops, whereas some of the ones that we are studying, Abell 2744, for example, we're able to get a much higher recovery fraction. Okay, and the key thing here is also that by doing high redshift galaxies, we can start studying things like the luminosity function here. And by looking at the luminosity function in different models, you can rule out different models based on how well they fit the luminosity function. So the data are these points here that we have Z of 10, but you can see that the error bars are big and the models are all these lines, and you really can't constrain this because obviously the error bars are too big to say any one of these models is better fit to the data. But soon we'll have many more points here that we can do. We can make much better luminosity functions and then constrain these models. And these models have different metallicities, different star formation histories, different IMFs, initial mass functions, different ideas about magnetic fields, different ideas about early galaxy formation. And so this will be a very exciting thing that we can do soon. Okay, so I think I'll just skip the CLEO cluster. This is just one of the clusters that we're going to study with Webb coming up soon. And again, this is one of the low light level clusters that we'll be able to see the background galaxies being magnified by quite a lot. And just to finish on Euclid, so Euclid is another telescope that I'm heavily involved with, and this shows the area parameter space for Euclid in magnitude limit. So this is fainter stuff, and then area, this is larger surveys. Euclid wide and deep here will be in a new regime of space in this plot, whereas Ultra Vista, the thing I showed earlier, in video, they're here. So this will be a whole nother regime where we're really going to be able to study these galaxies in a large area in a way that we haven't before. Okay, so just to summarize, galaxy formation is driven by mergers. and we're just starting to quantify the role in galaxy formation. And we can see minor and major mergers up to redshift of 3, and even at higher redshifts for the majors. And I'm sure minor mergers exist at redshift up to 6 or more, but we just can't see them yet because we don't have enough good enough data to do it. But Webb will help with that. It's not the dominant method for formation of galaxies, but it's at the 25 to 50% level. And star formation is more important, as I talked about. But at the highest redshifts, we know that it's the mergers which are becoming more important. And this is important for these gravitational wave predictions. And then finally, JWST will really answer some of these questions in a way that we can only really start asking for the super high redshifts. Okay, I'll finish there. Thanks very much for paying attention, and thanks again.
Thank you, Chris, for such a useful talk. So now let's have some questions if there are. Okay, I have a question. When you are measuring, especially the minor merger rates, so there can be a lot of what is the error that can creep in because it's photometric redshift. So they might be just in the line of sight and not merging, especially even if for major mergers, maybe you can get a very good redshift for both of them. But in minor mergers, how do you deal with that kind of error?
Yeah, that's a good question. So let me see if I can, actually, I had this plot here in case that question came up. So the way that we do this is you find two galaxies close together in the sky, like here. And then we have a photometric redshift probability distribution function, P of Z. And the two examples are shown here, where you have the red and blue for two different galaxies. These are the PDFs of the redshifts, okay? And by doing this, you can come up with a method, and I don't have time to go into it, but basically it gives you a probability of the thing being actual real pair. And so you're right that the photometric redshifts may not be as good for the fainter galaxies, the minor mergers, but that is reflected in the quality of the photometric redshift probability distribution function. They're not as good, but statistically, what we're getting is probably correct because we're taking into account the fact that they're not as good. But if you also look at what we're doing for the plotting the minor mergers, we're only going up to redshift 2, redshift 1 for the lower mass galaxies, and so we're not probing super deep, making claims at a very high redshifts where we don't have the good data. So I'm pretty confident that what we're getting is more or less right.
Okay, okay. There's a question in the chat that's about how accurate are JWST redshifts going to be? How would they make things better in terms of these merger rates?
So James Webb will allow us to get very high quality imaging and then therefore photometric redshift distributions for galaxies up to redshifts, well, as high as that we can see them, maybe redshift 15 or so. And because the data is inherently different from Hubble in many ways, and the fact that it's longer wavelength data, it's going to go into regimes where Hubble cannot, that is greater than about 2 microns rest frame. Sorry, observed filters at greater than 2 microns. That's about the K band, the red part of the H band. That will be able to really probe the spectral energy distribution in a way that we can't do now for these very distant galaxies. Now, if you want to study the SEDs of these distant galaxies, you have to use Spitzer data, and Spitzer data is very hard to use, simply not only because of the depth issues, but more importantly because the resolution is really not great, because the telescope was a relatively small mirror compared to James Webb. And so you get these blurry images, and so trying to measure photometry accurately is very difficult. But Webb will give us very, very high resolution. So we can measure very accurate photometry. So the SEDs will be well characterized, but also Webb is really, you could argue, more of a spectroscopic telescope than imaging. And so it's going to measure spectroscopy for so many galaxies that we can actually use spectroscopic redshifts instead of photometric redshifts. And then that will really improve how we do this, because we'll have many more spectra and absolute redshifts than these estimates from the photometric redshift. So I think it'll help a lot.
Okay, there's another question in the chat, and that is like, if you would be biased towards observing only merging galaxies because those are brighter at high redshift, so that can have an effect on the merger fraction that you measure as a function of redshift. Yeah, that's the question.
Yeah, there's a few things about that question. So the first thing is that when we do these comparisons, we're always comparing galaxies at a given stellar mass, okay, that is 10 to the 11, 10 to the 10.3, or so, 10 to the 10, and we're only looking at things to where we're complete in that mass range. And how do we know we're complete? Well, the data is deep enough for even the reddest galaxies to be detected, even the most difficult galaxies to find, which are not undergoing star formation, which are dusty. Now, there could be examples of galaxies that are so dusty that we may not even find them with our imaging. And we do talk about that in some of our papers, but those galaxies are extremely rare. You do see them. So if you look at like submillimeter experiments, looking at deep fields, you do see them, but they're really rare. They're maybe not even 1% of the sample. So I don't think it's a huge issue. The other thing about this is that it's quite controversial whether or not mergers trigger star formation. You see lots of star formation which appears to not be triggered by mergers. And there's a lot into this question as well that I won't have time to talk about. There's a lot of things going on with it, but in general, you have papers which clearly show that there's not really a strong increase in star formation for galaxies due to mergers, and that they're not necessarily always undergoing mergers. And that could be different at the very high mass end or very, very luminous galaxies. But your general galaxy undergoing star formation is not induced by the merger process. I don't think it's a major issue.
Thanks. There's another question. You showed that the outer radius is increasing more than the inner radius, and you say that that is one of the evidence for major mergers, but for mergers. But that is also given as an evidence for accretion that is settling on the outskirts. So you only see an increase in the outer radius. So so it could also be that, or what do you say to that?
Yeah, that's a good point. So that indeed could be true. So what I don't know is if you simulate a galaxy which is accreting mass from the intergalactic medium, where that gas would be where it would be deposited and where the star formation would be triggered. So a lot of the star formation that is triggered, the star formation to be triggered, the gas has to be dense and cold. That's really the criteria. And so the gas falls into the galaxy is more likely to be triggered sort of towards the center of the galaxy rather than the outer parts of the galaxy. Whereas if you create another galaxy, the process of the merger will often distribute that material more in the outer parts of the galaxy, making the new remnant larger due to the existing stars. So it's just the way that collisional and collisionless stuff kind of interacts dynamically in a galaxy. It can be quite complicated, but I think the gas falling in is more likely to go towards the center.
Okay, but even in secular evolution, it is said that if you just leave a galaxy on its own, it will just become more concentrated in the center and the outskirts will expand. So that could also be playing some role here.
Yeah, that's perhaps true, but I don't think the effect is as large as what we're seeing. You overall see that galaxies will increase their size at a given mass by up to a factor of 5, from redshift 3 to 0.5. So that's a huge amount of increase in size.
Can I ask a question?
Go ahead.
Very interesting talk. I don't know whether I've understood it correctly. When you set up the evolutionary equations for the gas mass increase and compared with the observational constraint that the ratio of the gas mass to stellar mass is roughly not changing over redshift, did you conclude that mergers cannot bring in the gas mass required to explain the star formation rate history? Is that
Yes.
what you concluded? Okay.
Yeah, so I would talk would have been way too long if I included all that. But yeah, so you have an idea of what the well, you know what the mass of the galaxies are merging. You know what they are, and you know what the gas masses of those galaxies are. You can infer what it is, and most likely what it is. You can give it a distribution, and if you consider that, it's definitely not enough.
So in
It's
that
not
regard, I was wondering if, I mean, we now know that the CGM contains a huge amount of gas,
Yeah.
baryonic gas. Is it possible that mergers, especially the minor mergers, can induce some sort of cooling in the CGM and then that can rain down and then increase the gas mass?
Yeah, that's possible. So I did say that it could be the IGM, the CGM, or cold accretion.
Has there
We
been
don't.
any work on this?
In what sense? Theoretical work?
A theoretical or simulation, bringing in mass from the CGM?
Probably is. I just don't know about it, to be honest. Don't work in that area very often. So there probably is something about it, and it would be good to discuss it with people who are experts in that area whenever I actually travel again to meetings.
Okay, thank you.
A talk here.
Thanks, everyone.
Thank you. Thank you.
Bye-bye.